Welcome to Open Networking TV. This is The Catch Up. I'm your host, Art Fuel, and today we will be catching up with David Mayer, who is, the chief grand poobah of OpenDaylight, among other things, and a principal. I'm going to mess this up. What's your title at Brocade now, David?
Service provider, CTO, and chief scientist.
And I'd like to just share with the audience a little bit about how I met you, because for me, you're you're the coolest, nicest, just example of what people should be, but in this open networking community. I first saw you speak at the first Open Networking Summit. First time really covering any of the, or going to one of these type of events. I had never been to IEEE, and everyone's in suits and ties and is so formal. You were representing Cisco at the time, and when you walked on stage, you came out in a T-shirt and a pair of shorts. It was so inspiring, as someone who's trying to be a technologist, trying to be honest about my work, trying to pursue technology for the sake of what it does, the great things that it brings to people, not wanting to get caught up in all the corporate crap. And to me, you showed me that you could be that. You could be that person who represented technology and great innovation, and still manage that dichotomy of having to be the corporate self too.
Yeah, well, I've never been very good at being anything that isn't just what I am. It's kind of a what you see is what you get story here.
I know you have a recent paper that you wrote, to response to Stephen Hawking and his colleagues regarding artificial intelligence and what that's going to mean, and some of the fears that we in society have about that as it evolves. Could you mind sharing a little bit about that?
So one of the things that I've been interested in recently is basically machine learning. And machine learning it's really a fascinating area to look at, and it's really exploding right now in terms of the number of different applications. And I mean, it's kind of the hottest thing around right now in a lot of ways. Everybody has some machine learning something, right? And my idea was this idea of software-defined intelligence. So basically, what I wanted to do was say, okay, we went through this whole SDN thing. Well, we're in process with SDN. But one of the things about SDN was it was really never the idea. Well, maybe it was in some cases, but I mean, many of us had the idea that we were going to be able to do new and interesting things. And in fact, these things became actionable because the network's now programmable. So the next step, obviously, would be how can we make the network, more intelligent, quantum leap, right? And obviously, machine learning is the way, or at least one of the ways to go and to get there. And so so I got into machine learning, and it took me a while to kind of understand what it was. And in the process, I learned that, I met this guy called Ben Goertzel, and this guy is an artificial general intelligence person, which is different than kind of the what's called narrow AI, or the kinds of things that you see happening, say in Siri, speech recognition, vision, different things like that. And at the same time, Stephen Hawking, this was back in March, I think, had a piece along with several of his colleagues, kind of worrying about the future of AI and could a malevolent super intelligence arise somehow by accident or on purpose, and what would that mean? And what are we doing about it? Are we trying to regulate and anything like that? And so I kind of wrote this blog, the one that you're talking about. I think I published it on Packet Pushers quite a while ago with Ethan and so the idea there is that should we be somehow concerned, and if we should be, what should we do about it, that artificial intelligence will gain what's called recursive self-improvement. In other words, are we going to build an AI that at some point starts rewriting its own code in such a way that it becomes 100, 1,000, 1,000,000 times more intelligent than humans? And then if it does it become malevolent? And Stephen said, there's no real physics that says that this isn't possible.
Right.
In other words, maybe human intelligence isn't the best intelligence, it's just the one we have. So I started looking at that, and I started looking at AGI, which is kind of on the fringe, of AI in a way. But I think it's the goal of AI in some ways, anyway. And so I just wrote this up saying, it's an interesting thing. And people like Ray Kurzweil, who's at Google now, are saying things like, oh, we're going to have AGI. So this is the artificial general intelligence, human-like intelligence, by like 2029, 15 years.
Yeah.
I personally, that will require some major breakthroughs, because when you look at the best state-of-the-art stuff in machine learning right now, like what's coming out of Andrew Ng's group, so they had a speech recognition system called Deep Speech that was built at Baidu Research, where Andrew Ng is now. And it gets it's state-of-the-art. It gets 16.5% error rate on transcription and things like that. So, the best is good, but it still has a ways to go. But those things are called narrow AI. They're highly engineered to solve a particular problem. Now, and they're not generalizable. Now, that doesn't mean they can't be components of what's called, AGI, artificial general intelligence, but they themselves are not. So what Stephen and his colleagues are concerned about is that somehow, either on purpose or by accident, that all of these components will be put together and an AGI will occur. And then what? Is that good? Is that bad? And that gets into all kinds of ethical questions and things like that. So my approach to it is something like, it's interesting intellectually, of course, but my approach to it is, let's work on machine learning. Let's see if we can bring that to networking. Let's see if we can make the way we do networking much more intelligent. And we'll worry about the AGI stuff later. That's kind of my approach to it. And like I was saying, in the case of what Ray Kurzweil is saying, that, it's 15 years, that will require major breakthroughs. But on the other hand, you could make the argument that these things happen by accident all the time. For example, somebody discovered penicillin accidentally.
Quickly to explore the other side of it, the one example that, I probably shouldn't comment on because I don't know enough about, but it stands out in my mind is I had watched a report, I don't know, a year or two back, and it was about the IBM Blue Brain project, and it was saying, they're essentially trying to create a large number of very, very simple systems that will simulate the behavior of a single neuron, and we're going to clump all these together in patterns that resemble, human brain, things like that, and hopefully it'll take a life of its own in a true, complex chaos system, and at that time, what they had said is, we're still a ways off, from doing like a full human brain size thing, but we have done this methodology to model a rat's neocortex. And once we put all of the randomly behaving neuron simulators in this pattern, it started to spontaneously take on its own kind of behavior as expected. I thought, just fascinating, right? I don't know what that's going to lead to, but it's a very interesting area.
Well, the whole area of neural networks is really interesting because, if you look at it, the neural network itself, it kind of has two, the machine learning on neural networks. By the way, there's a billion machine learning algorithms. That's another thing, is that there are so many of them and, hundreds of new ones every year, which makes you kind of think the field isn't, is kind of still kind of trying to triangulate on where it's going to go. But the neural network stuff is really interesting. And one of the, it kind of has two parts, right? One is that the neural network itself is this incredibly powerful computational device. It's really hard to imagine what it can't do, right? On the other hand, it gets trained by an incredibly simple algorithm. You need to know a little vector calculus, but if you've gone through upper division, this learning algorithm works in a couple of hours, probably. The thing is that what it does is it generates an incredibly complicated program that you don't know how it works internally. And that's kind of a little bit, I wouldn't call it magic, but well, maybe this is the same thing. It's not well understood.
I was watching a new TED Talk the other day where somebody was talking about a lot of new machine learning applications or deep learning applications. And I think a couple of examples that they highlighted were, I think, fairly visible this year. One of them was there was a conference in China where Microsoft was presenting and had a computer kind of do a real-time natural language translation using a machine learning-based algorithm. And that was really fascinating. While I was listening to the talk, they were saying, basically what they did is, you can't necessarily program a computer to do everything, but you could teach a computer to learn how to do something. So they had a team of Swedish people that created the best algorithm for translating Chinese, even though they didn't speak Chinese, because they taught the computer how to go learn Chinese. Is that a good example of kind of...
So one of the things that people typically don't understand about this technology is that, when we write code nowadays, basically what happens is you write some program, you give it some input, and it gives you an output, right? So, your routing protocol receives a packet, that's input. You have a program running in there, does something to the packet, sends it or drops it, right? So what machine learning does is something very different. What it does is it takes data and a machine learning algorithm and outputs a program. And the objective of that program is to generalize whatever it's doing. Usually either classification, it's an A, B, or it's a C, it's red, it's white, or green, or whatever. Either classify or compute a function or something. So it outputs a program that you hope generalizes to cases that you haven't seen yet. That's a very different paradigm than, what we're used to. So, as you were saying, in the case of processing language, this is a very good application for machine learning, because what you want to do is build a program that when it gets a new set of words or sentence, it will be able to interpret those even though it hasn't seen it before.
I'm curious, as we apply those techniques to computer science and to networking, how would you apply like a machine learning or deep learning technique to a network analysis?
Oh, yeah. I mean, one of the things you'd want to do, there's some really kind of low-hanging fruit things that you want to do. Oh, by the way, let me say one other thing before we go on with that.
Sure.
Is that machine learning people have this saying, and it says that, basically the person with the best data gets the wins, right? Mm-hmm. And the reason why is because, again, in machine learning, what you do is you take data and you take a machine learning algorithm and you put it together and you get a program. Right. And in the case of a neural network, the program is actually consists of the weights that are on the neurons. We can talk about what that means. But basically, it's a program. It's a program. And so the better your data is, the better your program is. And the people with the best data, like Google's and things like that, get the best results. Because you have to train the neural network to learn this stuff, right? So let me give an example of some of the things you might want to do. How about, so what you want to do is you want to say, I built a neural network that can predict something based on inputs, right? So there's some non-trivial correlations that you can't see in your data that predict something that you're interested in, right? Well, what are those kind of things for networking? Well, they're kind of, congestion occurring, packet loss occurring, anomaly detection, anomaly, DDoS prevention, all of these kind of things like that, where what you want to do is you want to take some data and use it as sort of an indication of something that you want to predict. That's a great machine learning problem. And so there's all kinds of machine learning problems in the network, which is, by the way, it's kind of surprising that that this hasn't been exploited more already. But,
right?
As I said, this is sort of surprising, right? Most of it's done in sort of like what you might consider to be like analytics settings, which are somewhat different.
Like you were saying earlier, the very idea of having analysis means that we need something to generate for humans to analyze. And kind of this interacting with a system that might be based on machine learning, it seems like it's already done that analysis. It's no longer trying to give you information to allow you to do the analysis. We're really talking about developing systems that are smart enough to know, okay, try this or learn from this, figure out the best way to do this. And when you think about the amount of cycles and the efforts that we spend, trying to figure that out, I mean, it really could be very revolutionary, right?
Right. So what you kind of touched on there is what I consider to be the difference between what you might call machine intelligence and machine learning. So machine intelligence is somewhere between here and AGI, right? Mm-hmm. Machine learning is a component of that. You have to be able to learn. You have to be able to build statistical models of the world that you see. If you think about how your intelligence works, you have all these sensors, your eyes, your ears, tactile, all that kind of stuff. What that's doing is that's throwing a big stream of data at your neocortex, which is then building statistical models that allow you to kind of understand the world around you. And actually the network's doing the same thing, right? You can think of the network, even the non-IoT network is actually a sensor network. So if you think about it, every, MIB variable, every, gang, field or whatever, all of those things are actually sensors, right? And so the network's just throwing off this massive amount of sensor data, but in some ways there's no brain to receive it, right?
Yeah.
And so what we're talking about is building that brain, right, to receive it, if you want to make the analogy to those.
That's a great analogy.
So that's kind of what we're trying to do. So you can think about sort of your own system as just a bunch of sensors throwing a bunch of data towards something that can build these models. And that's what machine learning is trying to do. And networking is just such an obvious place to try to do it. Again, as I said, I'm kind of surprised that people haven't done it yet, but maybe, there's more low-hanging fruit that, machine learning researchers want to pick off first. So before I go on, there's been some breakthroughs over the last decade that make this possible. If you rewind to, say, 2005, basically the best researchers in the machine learning field were not being successful in training these deep architectures. They couldn't get it. They couldn't do it. And they had made a fundamental mistake, which had to do with the scale of the randomization that they used for randomizing for initializing the weights on these things. So they just had made a mistake and they couldn't train them. And so there was a breakthrough by Jeff Hinton and his crew, I guess at Toronto, where they realized this, among other things, and started being able to train these deep architectures. And these deep architectures are really powerful and really expressive, but you got to be able to train them in order to get this. So this is all in the last 10 years.
For me, I had this kind of light bulb moment. This was a few years back, and I was taking this statistics course, and I was reading through the book, and it was like, the further you go back in the history of statistics, it seemed like you could see very clearly there was huge distances of time between one innovation and how we might calculate statistics, and then the next guy that they would talk about in the textbook, and the next guy would be years later. And as you get closer and closer to modern stuff, you see the frequency increases. What they would do is they would come up with this hypothesis. They'd go out and they'd have to get it validated by the community, and it would take, depending on time, decade, 20, 30 years to get enough validation to think, okay, but we accept this, we can move forward. And it seems to me, as I was taking that class, you could do that same validation now in R by yourself. Rather than, you don't have to go out to the community to say, is this a valid statement anymore? And it is profound, the impact that that'll have.
Yeah, so, part of what makes that possible, by the way, is the network that we built, right? Mm-hmm. But, one of the things that you'll notice is that in machine learning, there are standardized image data sets, handwriting data sets, speech data sets that you can actually benchmark or build your learning system and then benchmark against that to see how well you've done. And so that's available to everybody. And like you said, there's R, but there's Python everywhere for everything you want to do. There's a ton of open source code out there, some good, some better, as usual. But you don't have to code up all these hard algorithms yourself these days. You can just go get them, right? Which makes access to this technology quite a bit easier.
And now, as I expect more and more vendors release SDN controllers, just one example, they're all going to inherently have really, really, really good high availability clustering in them, which is something that's been really, really hard for a long time. I think it's because, you guys are figuring it out, the other PhDs of the world, right? And then releasing it through open source and helping to create this paradigm to where vendors can accept, okay, here's going to be the new norm. Let's all establish ourselves around that new norm. And it benefits the entire community because now we'll all be able to easily get access to applications that weren't even feasible for most of us a few years ago.
Yeah, it's very true, and it even goes further in machine learning. I'll just bring it back to machine learning.
No, please.
It's kind of interesting. You can now there's all these open source projects, but one's called Craft at Berkeley, right? And in there is an already trained convolutional neural net for image processing that's been trained on one of these benchmark sets. So if you want to do image processing, you don't have to train it. You can just go get it, right? So these, that effect that you're describing has already permeated the machine learning community, right? So if you want to do a machine learning project where, let's say, here's an excellent machine learning problem. Somebody comes to you and says, I want to build a product where what it does is it opens the door, the cat door on my door to my kitchen only when my cat shows up. That's perfect machine learning problem, right? You can just get code that will help you identify your cat and do whatever you want to do. You don't even have to write that or train it. It's already available. So
it's profound, right? I mean, when you think about how that might apply to something like security, if let's say malicious individuals were to somehow really be able to apply machine learning effectively to hacking, it starts to become apparent how this thing can waterfall, right? Because if there's some, machine learning hacking entity out there that it'd be hard for humans to be able to respond to, then you need a machine learning based counter to that, because that's really the only way to deal with it. And you can see how things can spiral from there, right?
Yeah. Well, I mean, I think that scenario that you described is unfortunately inevitable.
Yeah.
It's inevitable.
It's part of the evolution. Hopefully we'll keep the good guys a little bit ahead of the bad guys, right?
I mean, it's happening right now. So it's inevitable.
Just circling back to the networking community for 2015, is there anything that you think is cool happening in the OpenDaylight community this year that you'd like to talk about?
Oh yeah, I mean, there's all kinds of interesting things happening in OpenDaylight and networking more generally. And if you just look at the number of really interesting projects going on in our networking space right now, okay, so OpenDaylight, Onos, OpenStack, now OVN. I don't know if you're trying to do OVN stuff.
I haven't had a chance to look at it much yet, but I'm eager to.
It's really fascinating and cool stuff. And there's just continual hardening. Basically code is getting better, which is what you expect over time, which means that it's more applicable, more scalable, more maintainable, more functional. People are writing new and interesting applications on top of various control infrastructure now that they couldn't do before. And this is all opening up now because, as I was saying earlier, one of the ideas behind the software-defined intelligence thing is that it actually, if you created some kind of intelligence that you didn't have before, whatever that happened to be, it's actionable now because the network's programmable, right? Mm-hmm. Before, I mean, we did some things, but it was always about like screen scraping with expect or whatever, and it was very not very functional. And now that's all turned around. So I think in 2015 we're going to see just all kinds of applications that are not infrastructure, not the core infrastructure like controller and all of that, but new kinds of functionality that people put on top of these things, some of which is obvious, like I was saying, traffic engineering or something like that, but some of which you just had no idea about, right?
That's what I'm excited to see, right?
That's really interesting because, the barrier to entry to this is non-existent, right? Mm-hmm. I mean, you can go develop it on, your favorite cloud provider, and you can run it against anybody's network now because things are standardized. So,
yeah, you can probably get a free account on the cloud provider, to do a lot of things that one might need to do. It's profound, right? How it's just like that question. I've wondered when I think a lot of people have been wondering since that phrase SDN started to become into our vernacular. Now that people actually have this ability, it's starting to exist. These abilities that weren't there before. What might we develop with it? And I'm, and that's partially applies to networking, but I think you can go beyond to thinking like, okay, today around 2 billion people on the internet. By 2020, around 7 billion people on the internet. What might we do? It's going to be an amazing time, right?
Yeah. And, I'll just tell you, not just because I'm working on this, because I have a tendency to get all excited about this machine learning stuff and just apply it to everything. Mm-hmm. But, I have a hard time envisioning a future in which machine learning is just not central to everything we do because it's scale, if nothing else, Yeah. And not only scale of a thing like the internet that you're talking about, but scale of data sets. Everything you do now is just data oriented. Big data is, I don't like big data as a term because it's like cloud, right?
Yeah.
But it's everywhere, right? And the way that you process this stuff is with machine learning. If you think about overlay, underlay, right? In the overlay and in the underlay, there's all of these counters or telemetry in the network, whatever they are, counters, packet loss, whatever, If you think about looking at those like kind of in a horizontal way, vertical, like if you just take a cut through the overlay, underlay, and look at that, all of the data in the overlay and in the underlay is sort of one data element. And then you have all of those going through time, right? Are there patterns that are in that data set? I'm sure there are, by the way, mm-hmm. that you can't see. We can't see as humans because we're not that good at pattern. I mean, we're good at pattern recognition, but not at that scale. Right?
Yeah, in a very small scale, right?
Yeah. Are there patterns in that data that machine learning can exploit to give us new and different kinds of insight and new and different kinds of control and new and different kinds of, control and data planes that we hadn't thought of before. And the answer to that is almost inevitably so, and so once you get this situation where what you can do is do this exploration, find these patterns using these really powerful algorithms, learning algorithms, kind of everything opens up. So it's inevitable that's going to happen because there's not another way to maintain competitive advantage. Actually,
no, it's too powerful. It's far too powerful a paradigm, and once in every application that starts to take over, it's going to be one of those things like if you're not doing it that way, not so much just deep learning, but where Google stands from a neural network, from an overall analytics standpoint, it's very much like that. They have what if your business competitor had a crystal ball and you didn't? Right? It's kind of like that. You don't really have that much of a chance at that point, right?
Right. In other words, it's inevitable for various reasons, not the least of which is you'll lose competitive advantage.
So what does this mean for humans? I mean, and I'm just curious about your take on, I think we're approaching a time in human history where, in terms of the tangible goods that we need to live, who's going to, put the roof over our head, who's going to go chop up the food for us, things like that. And we're really at a point where we're starting to have to think about, at some point robots are probably going to be able to do most of the things that need to happen for the lights to turn on. What happens to humanity at that point?
So there's a really good World Economic Forum paper written by Nouriel Roubini at NYU talking about what happens just this scenario, right? And his conclusions are, a lot of even the skilled jobs that exist today are going to go away. One of the examples he gives is radiologists. So radiologists look at these X-rays, right? An X-ray is just a piece of data, right? And what they try to do with the X-ray is detect patterns. This is ideal machine learning. So, your local doctor probably doesn't do this, but large-scale medical things, what they do is they send these X-rays to India to have them read. Yep. Just like you send code there for all that reason. Have that read by Indian radiologists because it's cheaper to do there, perhaps. But now it's going to be even cheaper because you're going to have a machine do it. So the idea that, you're reading x-rays and that's your skill is not something that's going to be around in the future. Same thing with a lot of legal work. Legal work is kind of like pattern matching, right? So here's a bunch of facts. Do they match this statute or whatever? That is also in danger. So when you think about it, when you think about what you're going to tell your kids, what should they study in college or what should they do? You have to kind of look at that closely, because there's a lot, automation is really a threat to a lot of what had been traditionally high skilled, kind of employment scenarios, So I'll send you that URL if you're interested in it. It's pretty interesting stuff.
No, I mean it is. I think it's going to be one of the big questions of the 21st century, right? I mean, is what happens? Because I mean, I know a lot of us would like to think, and hopefully this will be the case, that we'll move more towards a more creative economy. I think there's been this historical view for a long time among the world leaders that life's about dividing scarce economic resources, and so let's go and genocide a population or something like that. And I feel like hopefully with technology we can get to the point of abundance, of being able to use machines to create more than enough for everybody, and hopefully get to a place where people can focus more on creative things, focus on their passions. Who knows? Maybe this utopian, a more utopian reality.
You can also take the Adam Smith view and see it as sort of a creative destruction, in the sense that technology always has a tendency to destroy some part of the economy while creating the new part.
And that's
so
it.
The trick is to know what the new part is.
And I think that part is certain. The question is hopefully the new part will be a part that's increasingly good for humans. And I know that, I mean, when you really take a well-informed view, nobody knows one way or another, right? But, I think we are definitely seeing today that there are a lot of new possibilities and a lot of new ways of solving challenges that we just never had before. So hopefully we humans can be a good, halfway decent, overseer of that while we're overseeing things until we're on the other end of that. Anyway, well, I appreciate your taking so much time with me, David, and I think the audience here will be just very interested in hearing all your powerful insights in the subject. It's one of the most fascinating of our time. Thanks for being on Open Networking TV. Is there anything you'd like to close with?
Not really, other than thanks for inviting me, and it's been a lot of fun.